let's get the recording right. I was just talking with Alex about where the book goes from here. So I have edited all 190 pages of what I had previously written down, but that's sort of half the book. And when I have taught, what is it, 6940, quantum field theory 2, I've been able to go twice as far, but I didn't get notes written down for that as the second half of this book. So Alex has volunteered to do some transcribing, because I have audio notes and pictures of the blackboard from the last time I taught that. And I want to get that written as the second half of this book. If any of you are interested in doing any of that transcription, that'd be great. If even if not, I have a feeling that you guys might enjoy doing quantum field theory 2 in some way or other, perhaps informally, where, you know, we'll continue. I'm not sure how we'll get. I hope we get to doing QED diagrams and, you know, actually calculating some transition amplitudes. That's usually my goal for the first semester. And, you know, we're moving along at a pretty good rate. So, you know, I think we should get there. But, you know, then we can go on into, you know, standard model things and transcribing over the summer. Okay, second here. All right. So we definitely have some interest in this. You know, let's, you know, Alex has started with 2 early sections of the notes. I can, Alex or I can share the link to where those are. But it's a little experimental at this point. It's not clear whether transcribing those notes or me just figuring out and writing it again is going to be the most efficient thing to do. You know, it seems like it might be really efficient to at least have those boards transcribed into licks. But let's see how this goes and keep talking about it. Yeah, I thought you know, would probably be interested in following through as, you know, as far as we can. You know, actually, oh, we might even touch on string theory. Who knows? But let's just play it by ear and keep moving through the material. So that said, we'll talk about those ideas. Now let's look at the negative energy solutions. So we have we divided this into these 2 equations. E minus m. Let's see. I've got to look at my notes here. Alpha plus sigma p beta. All right. So from the Dirac equation, recall yes, Lyle. Then minus sigma dot p. You've been reading my door, right? Wait a minute. Yeah. Okay, so now we want to solve these again with energy less than 0. So we've done the positive energy solutions. If the energy is less than 0, then E minus m is negative definite. No, wait a minute. Yeah, minus E minus m. No, that's not right. Are these the right equations?
That was the question I was going to ask you.
All right.
In the previous section, you had a pair of independent equations, one for U and one for V.
Right. Yeah. Yeah. So
And
Yeah,
it
go
doesn't look
ahead.
like and when you looked at is that the positive and negative solutions that you're looking at, or are they in the same like independent equation? That's my question.
All right, so yeah, what we get. So all right, what we're writing here. Let's just check. Gamma A PA minus M acting on the spinner part. You know, this could be U or V here. One or the other equals 0. So let's say we let psi be. Oh, okay. Yeah, there is a difference, isn't there? Yeah, we get two different equations. So these might have been for U. So we're letting psi be U e to the minus I p dot x plus v star e to the I p dot x, where p dot x is p alpha x alpha. Okay, am I writing large enough for you guys to see? So yeah, let's take it again and write these carefully just to see. So we wrote out the I d slash minus m psi. That's our equation. We're going to expand psi that way. So what we get is, all right, I gamma mu, then partial d is going to pull down minus I p mu, and then leave the u minus m u e to the minus I p alpha x alpha. That's this acting on the u part. Then we have I gamma mu, and now this is going to pull out a plus I p mu v star minus m v star e to the minus the plus I p dot x. Okay, check me as I go here. So we want that to be 0. So for the p equation, you know, this is p slash let's see, should be like that and that. Can I get it right here? Do the same thing here, like that. Okay, check me. Are we good here? Then this is going to be plus p slash minus m u. These modes are independent, so this vanishes and that vanishes. And then for v, we're going to get minus p slash v star, well, minus m v star equals 0. So these are the negative energy solutions. These are the positive energy solutions. Here, all right, p slash, all right, gamma mu, p mu is p slash, and that's going to be, right, the 0 component gives the energy, and that's going to give us E and minus E here. Then off diagonal, we have P dot sigma and minus P dot sigma. Check me on this. I'm going off my memory here. Then we have minus M here. And that's that whole equation. And then we wrote U as an alpha beta thing. And so we had E minus M alpha plus P dot sigma beta equals 0. And we have minus P dot sigma on alpha minus E plus M beta equals 0. So we solved the second equation for E greater than 0. this is all recap basically, but this is looking like what we had. I can solve this so we get this matrix operator P dot sigma over a positive number E plus M acting on alpha. And then we chose alpha to be either 1, 0 or 0, 1 to get two independent solutions, and beta is then determined by this. And we had the condition E squared minus P squared minus M squared equals 0. Since we chose the positive solution here, I defined omega to be plus the square root of P squared plus M squared. And I'm going to hold that through both solutions. But in this case, E is equal to omega. Okay, everybody up with the positive energy solutions. Any questions on those?
That looks good to me. Real
Okay.
good.
Okay. Yeah. Eli's looking stoic and I can't see Lionel, so I'll assume they're good too. All right. All right. Now, this is acting on V. This time, the equations for V, we've got minus V minus M, so it's going to be plus M. All right, so we have, just multiply by a minus sign, we have P slash plus M. So the matrix equation will be E plus M P dot sigma minus P dot sigma and minus E plus M on alpha beta equals 0. So now we get, again, two equations, E plus M alpha plus P dot sigma beta equals 0. And here we go. This looks better. Minus P dot sigma acting on alpha plus minus E plus M on beta equals 0. All right. This allows us to solve, well, we solve for beta again. If E is negative, then minus E plus M is positive definite. Oh, there's Kevin.
So here we're solving the 4-spinner V star.
Yeah, that's right. Yeah, yeah, that's right. This is V star now. Just a different alpha and beta. There's just a convenience for getting a solution. Oh, okay. All right. I can. Yes, sharing is caring. Hi, Kevin. So we can solve for beta here by bringing this to the other side and dividing by this positive definite quantity. So we're going to have P dot sigma over, so let's call this minus omega. So omega is now minus E. So this minus E becomes the positive omega plus M. And then that's acting on alpha. So once again, we get two solutions. If I put this into the top equation, then we have minus omega plus M alpha, let's see, so that's P dot sigma, wait a minute. Oh, I'm doing it backwards, sorry. Alpha plus, okay, beta here is P dot sigma squared over omega plus M was our solution times alpha equals 0. Okay, that looks good. So now we get, if I multiply here, we're going to have minus omega squared plus M squared plus, remember P dot sigma matrix squared is just P squared. All times alpha equals 0. And so once again, we get omega is square root of M squared plus plus p squared. And we've already taken e to be the negative root. So, so we satisfy the whole set of equations now for any alpha. And once again, we're going to choose alpha to be either 1, 0 or 0, 1. So this gives us 2 positive energy and 2 negative energy solutions. And I'm probably standing right in the way here. 2 positive, 2 negative energy solutions, where for positive energy, we have 2 solutions. For negative energy, we have 2 solutions. And if we write these things out, then let's go ahead and do that. Can I erase like the top half here? Scream if not. No screaming. Okay. So we have U1. The first solution for U is when we take alpha up. So we have 1 and 0, and then beta, right? This matrix here, let's write this out. So the matrix we're working with in both conditions, P dot sigma over, in both cases, it's omega plus m in the denominator. And then we'll have an overall minus here. But that matrix is 1 over omega plus m. And then P dot sigma is Pz minus Pz times sigma z. And then for sigma x and sigma y, we get Px plus IPy and Px minus IPy here. So when alpha is 1, 0, we're going to pick up the first column here, and that'll be Pz over omega plus m. But we have this minus sign, so it's minus that. I missed that in the notes. I fixed it now, but I haven't posted that yet. And then again, the minus, and we have Px plus I Py over omega plus m as the first U. Then we have a normalization here. I think it's omega plus m over 2 omega, but let's just check the normalization. So if I write U dagger U1 dagger H U1, that's the norm. H is our metric. Remember, H is 1, 1, minus 1, minus 1. So this is going to be, this is just going to give us 1 and 0. And then we're going to get minus the squares. It'll be this times the complex conjugate. And let's see. In the first case, it's minus. Then when we act with H, it's going to be plus. So we're actually going to end up with a plus or a minus. Yeah, this is going to be straight minus here. Then we get some minuses from that, and then we get more minuses. So it ends up being minus, and we're going to have Pz squared plus Px. Well, it's just P squared here plus Py squared, because we take the conjugate in U dagger over omega plus m quantity squared. And if we work that out, this 1 gives me omega squared plus 2 omega m plus m squared, then minus p vector squared here, all divided by omega plus m squared. And now omega squared is m squared plus p squared. So I'm going to get 2m squared plus 2m omega over omega plus m squared. So let's see. I can factor out an m plus omega here, so I end up with 2m over omega plus m. And so what goes here is the square root of 1 over that to normalize omega plus m over 2m. Okay, questions, normalization, everybody good there? You know, you just normalize it. Okay, then U2, I'm gonna, let's see, where can I fit it? That's right, U1 and U2 here. And so I have room to do V eventually. So the second one, we're gonna pick up this second column when we act with on alpha equals 0, 1. So it's going to be the same, and I'm pretty sure the normalization is the same on all of these. We're going to get 0, 1. And now, all right, we have our minus signs and our omega plus m, and now it's px minus I py. And minus pz becomes plus pz with the minus sign, with this minus sign, and that minus sign we get plus. So those are the positive energy basis spinors. All right, at any positive energy and momentum p. So you can show, and I ask you to show some properties of these in the exercises, like show that they're orthonormal. There are various relations between the U's and the V's that I want you to prove. Give you a chance to just work with these spinors a bit. None of those exercises is hard. You know, just writing out these components, checking normalizations, and that sort of thing. Okay, so that's the positive energy solutions. The negative energy solutions, very similar. We've got some sign differences and things. Let me see. Here's our solution here. So I can start writing V star up here. So V1 conjugate ought to be, and I'm pretty sure we always get the same normalization. I'm just going to write that, and yeah, that's what my notes say too. So yeah, you can actually get m minus e here, so the minus e turns into a plus omega. Then the spinor itself, right? Now we put in alpha down here, 1, 0 that way, and now beta is just positive this on alpha. And let's see, I wrote out p dot sigma over omega here, so we're going to get pz and px plus iy over that denominator, pz over omega plus m and px plus I py over omega plus m. And then the conjugate, or sorry, the second component is going to have these two. So let's see, where can I write that here? Make room here. So we get all 4 of these on the board at once. The 2 conjugate is omega plus m over 2m. And now we're going to have px minus I py over omega plus m minus pz over omega plus m and 0, 1. Now let me point out something that we will prove shortly that is a little surprising, but we need to do that. All right, suppose the particle is at rest. Then then here, right, P is 0. So these two terms are 0. And we just have basically what's familiar as a spin up and spin down two-component spinner. And that's exactly how this plays out. When we look at the Hamiltonian, and then we will define spin operators, and we can measure the spin of these things, and you get h bar over 2 and a +1 or a -1 as eigenvalues of that spin operator. Okay, and positive energy. Then on the V states, we could just take the complex conjugates here if we wanted. That might actually be nicer. Why don't we just do that? Because there's only the one sign here, and that becomes plus. The spin up and down states for the negative energy states. Okay, if you look at the Hamiltonian, these are negative energy states, and these are spin up and spin down on the second two-component spinner, but this one is the spin up, and that one is the spin down. So it's component-wise, spin up, spin down, spin down, spin up, and we'll see that emerge necessarily as we work with the gamma matrices and stuff like that. So there are normalization conditions on all these. I ask you as exercises to show that, let's see, there are a couple things that the U's and B's. Okay, when I write something like a U, V, say I and J, like that, right? That means U dagger H V. The I equals 1 to 2, J equals 1 to 2. These turn out to be 0, and I ask you to show that. It's taking a dot product of some 4-component vectors, and if we've done this all right, then that'll just work. The other identity that turns out to be important is if we take outer products of these, I can take these form a complete basis. If I were to take the outer product I with I plus J hat with J hat plus K hat with K hat, right? You guys know what matrix that is, right? That's the identity matrix. If I've got a complete orthonormal set of vectors, I can build the identity out of them, and so we're going to do that. But what we end up building is the metric. Okay, so no, I'm sorry. I said that wrong. If we take U, I, the A component, and U, J, the B component, to build a matrix like this, and we're sorry, I and J. We're summing over these, but you need minus the I, A component, the I, B component. So it's that product that gives you the identity there. So so exercise show that actually works out to the identity. All of this, you need to do these exercises, right? What happens is that we're going to develop some projection operators that let us, use gamma matrices in various combinations to project U1, U2, V1, V2, any component of these basis vectors we want. And that's really handy because two things happen. When we build the matrix element for a transition amplitude in a Feynman integral, what you're going to get a product of a whole bunch of different fields. So you may have an electron, a spin up electron coming in, and a spin out positron going out, and some other stuff, and you're going to multiply all these fields together, and eventually you end up you've got a couple of spinor fields on the end of some long expression with gamma matrices in it. If you have these projection operators, so you have a spin up electron, well, then you put the positive energy spin up projection operators built out of gamma matrices on a general spinor. And then the outer product of general spinors on the ends of your expression turns into an identity and gives you a trace of the whole thing. The whole thing becomes a product of a bunch of gamma matrices over which you're taking a trace. So these identities that let you replace outer products of spinors are ultimately going to let us replace all of these basis spinors by products of gamma matrices and take a trace of those. So, we'll get there. That's Feynman rules and stuff. And, we have to talk about scattering and things first. And I have to dig into my old notes and figure out how all this is done. But this does let us write a complete solution now to the free Dirac equation. And all right, I've written it in the notes with deltas on energy. So you've got a delta of E minus omega times the U states and a delta of E plus omega on the V states. And you add that all together with some arbitrary amplitudes. And then you integrate over those delta functions and you end up with integrals over K. So I'm just going to write the integrals over K here rather than do it in 2 steps. Are there any questions? You guys, everybody with me here? Yeah, I see. I don't see Guillermo's head, but I see thumbs sticking up. No, it's like, relax, you're fine.
Yeah, okay. Professor, is that expansion, that completion expansion, is that true for any orthonormal regularized complete set of vectors? It looks like you took four vectors that are all independent and outer product them, and since they're normal, is that a general way to construct the identity operator?
There's going to be some way to do that. If you have a complete orthonormal set of vectors, you can take their outer product. We've been doing this all along in quantum mechanics, right? Mm-hmm. So we've got some continuum basis of, say, momentum eigenstates. And we take the outer product of the vectors, we integrate over all momenta, and that's the identity, right? It's the same thing we're doing here. Only we've just got a 4-dimensional space, so it's just 4 terms.
And the sign is presumably coming from H, that it splits negative on both sides?
Right. Yeah.
Cool. Thank you.
Yeah, this funny sign is remarkably necessary. I was trying to, convince myself about the necessity for all of these things back when I first talked about spinors and things and, spin PQ. And I found a metric for any dimension, any signature, and it's always got trace 0. So the spinor metric is always trace 0. And by metric, what I mean is a metric such that if I have a conjugate spinor and a metric and a gamma matrix and a spinor, I want to define a real 4 vector that way, or I want to be able to define a real vector back in the vector representation of this spin group. So, we got here, remember, by looking at orthogonal transformations. That's OPQ, right? Any dimension, any signature. And so there's some vector space with a PQ signature metric that, leaves real vectors, gives us an inner product on real vectors. We need to be able to get back to those vectors from spinors now because we're talking about the covering group. All right, so what does this mean for this H? And what we know is that the rotation matrices are exponentials of some real parameters. Let's see, let's call it, what do I want to call this? No, let's just put some real parameters AB, sigma AB, where I'm double counting, so I put a half. Sigma is the commutator of two gamma matrices. Those we showed are generators of rotations. So if I put a lambda here and a lambda dagger there, this needs to turn into my SOPQ transformation of this matrix, and it's going to be a 2-to-1 cover. So whatever parameters I have here, they're going to come in twice and give me a rotation by a whole unit here. So that half comes out in some double angle formulas. Now, to get the PQ, some of these are Hermitian and some of these are anti-Hermitian. Otherwise, some of the gammas, some of your original gammas, to get a PQ signature, the ones that mix time-like and space-like, the commutator of a space-like gamma and a time-like gamma, has to be Hermitian, whereas two space-like or two time-like have to be anti-Hermitian. Otherwise, you won't get rotations or boosts. And that works out if you have certain commutation relations between H and these sigmas, which translates into certain commutation relations between H and, well, the gammas. I forget which way it goes, but it's in the notes. One's commutation, one's anti-commutation. So you need to be able to construct a matrix H that commutes with half these generators and anti-commutes with the other half. And basically, you can do it with, essentially what you end up doing is taking a product of all the time-like ones. So in space-time, you've just got gamma 0 as the only time-like one, and that turns out to be a good candidate for H. It's got the right commutation and anti-commutation relations with the other ones. In higher dimensions, where you've got multiple time-like dimensions, you take the product of all the time-like ones times some coefficient, possibly I to a power. Depends on the dimension and the signature. But you can construct this, and I checked, it's always traceless. So you always have this indefinite metric in the spinor space. That could be interesting for some reason. Actually, I use it as one argument that, you know, in a little while, when we compute the Hamiltonian and the what do we compute, the charge operator for these spinners, you know, we're going to find some positive signs and some negative signs, and those signs ultimately come from, in part, from the fact that that's an indefinite metric. But the signs are wrong unless you assume that spinners anti-commute. And that's the exclusion principle. The anti-commutation of spinor fields prevents you from putting more than one in any given state. If you have two spinners in the same state and they have to be minus themselves when you flip them, that thing squares to 0. So spinor fields square to 0, and it's a consequence of this indefinite metric, which is a consequence of group theory. So, you know, and Clifford algebras and Lie algebras and, you know, like all that stuff. But, you know, it's a deep mathematical result that forces us to impose the anti-commutation of spinor fields. And that has the physical consequence of the uncertainty of the exclusion principle, which means we can exist because now there are atoms with structure and all that, nuclei with structure and quarks with structure and all of that. So, you know, actually it turns out that is sort of interesting. Now, I want to be able to decompose these spinners. So as I was saying a little earlier, I want to build projection operators out of the gamma matrices in such a way that given a general spinor, I can if I want to talk about a spin up electron, I need to project to positive energies and spin up, you know, or a negative energy spin down state. I want to be able to project to that component. So I'm going to build two projection operators here that do that. And one of them is really easy because it's the Dirac equation. So let's start with that. Okay, well, I hate to erase these guys, so let's leave them up for a little while. I don't know if we're going to need them, but having written them, they're kind of pretty. Okay, yeah, I've never seen anybody talk about that that spinor metric, let alone find it in every dimension and show that it's zero trace. That's a new result. Somebody write it up and we'll publish it. Anyway, Dirac equation, I d slash minus m psi equals 0. So now we put in the various modes, so we end up with, I just erased it all. Let's see, minus p, so p slash minus m psi, right? And this is true for the u state. Yeah, this is right. Either of the u's gives 0. Okay, and then we have p slash plus m multiplying through by a minus sign on the v states gives 0. And these project out. These are eigenvalue equations, right? This says that p slash on a u gives m u. And this says that p slash on a v gives minus m v. So having eigenvalue relations like this allows us to immediately construct some projection operators. Partly because if I take p slash squared, all right, what is that? That's p mu, p nu, gamma mu, gamma nu. This forces symmetry on these guys. So I can write this as a half p mu, p nu times the anti-commutator. Stop me if you want me to go into any further detail on this, but that's just twice the metric. And so the two cancels and we just get p mu, p mu. So we get so p slash squared is p mu. That means that if I take the identity plus, now I need to normalize it by, all right, p alpha, I'm going to normalize and then p slash. Suppose I take half of that. All right, that is, well, that's clearly some matrix. Look at p squared. I've mucked this up so that when I square this, it's going to come back to itself. Right? I have a quarter, and then when I square this, I get, well, a 1 squared is 1. Then I'm going to get two of these guys, 2 p alpha, p slash, and then I get this term squared. So 1 over p alpha. Oh, I think I want the square root here. Sorry. P alpha. So I square the square root, then p slash squared. And we just showed that p slash squared is p squared. So this is 1 again. And so I get 1 plus 1 here, cancel one of them and I get a half. 1, and then that 2 gives me 1 over magnitude of p slash, like that. And so p squared is p, that means p is a projection operator. And it's easy enough to see what happens. The eigenvalues of p are going to be m. The magnitude of p is what's p alpha? P alpha. All right, that's e squared minus P squared is M squared. So this denominator here is just M squared. So that could have been easier. I just need a 1 over M here. Okay, so this is a projection operator, and you can see that if P hits a U type thing, it's going to pull out an M, and I'll get 2 over 2. If P hits a V type thing, I'm going to get minus M, and I get 1 minus 1 is 0. So P acting on V is 0. P acting on U is U. And that's a positive energy projection operator. What's the negative energy projection operator? What?
I'm just going to have to guess it's just going to swap the 0 and the U. Or V, like PV is going to be V and PU will be 0.
Yeah, that's what we want. How do I write the operator?
Oh.
Right. Here's how I write the positive energy projection. How can I write a negative energy projection? Yeah, did you do that?
Do you just do the minus?
Yeah. So if I put minus here, that gives me the negative energy. So look at what happens, right? So if I have the minus and this hits a V, I'm going to pull out a minus M. The 2 minuses make a plus, and that gives the 2 that preserves V. So P plus on U is U, P plus on V is V, but then P minus on U is 0, and P minus on V is V. So we have a pair, a disjoint complete pair of projection operators. Notice if I add these two together, I just get 1. So they span the whole space. They split it in half. It's really pretty clear what they're doing, right? In fact, let's see, is there, yeah, all right. Another way to see what's happening here. Look in the rest frame. In the rest frame, P alpha is just M and 0, which means that U is going to be 1, 0, 0, 0, and the other U is 0, 1, 0, 0. Here's another way to build projection operators. We can build a projection operator the same way we built the identity matrix, by taking outer products of spinors. If I take, let's see. Suppose I take U, I, A, U, I, B, sum I equals 1 to 2. Right? What is that? Well, in the rest frame, that's 1, 1, 0, 0, right? Just outer products of these vectors here. That's a projection to the first 2 components. All right, that is a Lorentz covariant projection from the full spinor space to U and to the U spinors. Well, it's Lorentz invariant, so that's going to hold in any basis, and I can construct these operators that way. If I write this out, and I write out this sum of outer products of these spinors, I should get the same thing, and I bet I will. I haven't done that in the notes, but if you want me to, I'm obsessive. I'll do that. So we have energy projections. And similarly for the V, if I take the outer product of the V's, that's going to project into the V part. It comes from the orthonormality. If I let this act on a VB, what am I going to get? Well, U and V are orthogonal. So that's going to give me 0. If I let it act on a U, all right, they're normalized, so I'm going to get a U. And so it's easy to see that that's a projection operator. But it's significant that we want to write it both ways, because this means that an outer product of basis spinors can be written using gamma matrices. That's what we're trying to do here. So if I have this outer product in some concatenated expression in fields, I can replace those outer products by one or more of these things. All right, now that's the energy projections. Let's look at spin projections. Are there any questions on the energy, guys? Everybody? Yeah, everybody's good. All right. Yes, thumbs and heads and yeah, good. Yeah, you got it. Great. Yeah, this is fun stuff. You know, it's not bad. It's really sort of cool that it works out so neatly. Now, oh, what is it I'm going to do here? Yeah, so you know, my first thought was that what I wanted to do, and yeah, this turns out to be interesting too. You know, if you want, there's another one of those. We know that the rotation matrices are sigma ij, given by the commutators gamma I with gamma j, with probably some normalization here. And I can write some angular momentum operators even if I take, you know, like a linear combination of those, then these satisfy the SO3 Lie algebra relations. Now, you might think that you could use that to build a projection operator. And so I did. And what did I call it here? Sigma plus or minus. And I take it to be a half and the identity. And now this thing, it turns out, if you find these commutators, these guys are diagonal. This is minus I over 2 epsilon ijk sigma k, like that. So these guys go like the square of those guys. The Pauli matrices all square to 1. So we're looking at something here, all right, once you get the normalization right, we're looking at something that ought to give us a projection operator. Well, it sort of does, but what I took was some linear combination of, how did I write it? Yeah, just, yeah, let's pick a direction and dot it into the J's here, like that. And now, if I square those things, you know, n hat dot j, if I've normalized my j's right, you know, that's going to be 1. So when I square that, it's going to come back to itself. You know, that really is a projection operator, but there is a problem with it. The problem with it is that we want to be able to project to the positive and negative energy states at the same time that we project to the spin up and spin down states, which means that these operators need to commute with the the energy projections. And that places a condition on this linear combination. Let me just write this as some, what did I call it in my notes here? Yeah, I just call it, let me just write this in components that way. So let's see what happens. If I take the commutator of a P with one of these guys, so if I take, let's say, P plus with sigma plus or minus, we can probably do both at once here. All right, that's going to be a half the commutator of 1 plus P slash over M with, well, we'll get a quarter out, 1 plus or minus N dot J, where J, remember, we have an epsilon, I need components here, Ni epsilon I, J, K, then this is basically a sigma jk. And so the ones commute with everything. That's not a problem. But what we're going to get here is 1 over 4m. Then we have a p mu, and we have the commutator of gamma mu with the commutator of gamma j, gamma k, which then contracts in an epsilon I j k and an ni. I've been sloppy about which indices this might be right, but gamma j, gamma k, let's just assume j is not equal to k. Okay, so sigma ij is the commutator gamma I, gamma j. But if I is not equal to j, that's just twice gamma I, gamma j. Right? You just flip the second one and it fixes the sign. So let's just keep j not equal to k. They're on an epsilon anyway, so they can't be. So so this is general enough up to maybe a factor of 2 or something. But the point is that this commutator does not vanish. In fact, it's going to give me an eta mu j gamma k minus an eta mu k gamma j times some factor. I'll put a fudge factor here. But I have a p mu now and an epsilon I j k and an n I. And let's see, this right, this is diagonal, so what's it going to be? This is going to give me a cross product. I see it. Right, so let's look at what's happening here. I have a p mu. I have an epsilon I j k n I, and then a gamma k, and then minus a similar term. But and there's an eta mu j. The eta mu j is going to give me the j component of this momentum. So I'm going to have epsilon I j k n I p j gamma k plus another similar term. The point is that this is not 0 unless n cross p is 0. Okay, that's the essential result I'm trying to get to here. The details are in the notes, and better yet, you can go work this out yourself. But the point is that the commutator of the energy projection with this instantiation of the spin projection is not 0 unless n and p are parallel. That's a property called helicity. And for a light-like particle, helicity is a Lorentz invariant quantity. The spin either aligns or anti-aligns with the momentum. For a time-like traveling particle, that is not Lorentz invariant. So what looks like a spin vector in the direction of momentum for one observer looks like the opposite direction of momentum for the other observer. It's okay. You can quantize the spin along the momentum axis. That's not always what you want to do, but you can. But it's not Lorentz invariant. It'll change if you do the right boost. You can get it to flip. So while this is sometimes a reasonable projection operator for null vectors, these guys have mass. These are electrons, not photons, and helicity is not really the thing you want to use. What you want is spin. So we need a different operator, and the thing that is going to work for us, we need something else, something else diagonal, right? We need something to form a projection operator. You need something that's going to square to 1, so that this thing squares back to itself. And one way to do that, if you remember, the spatial parts of the gamma i's look like this. And gamma 5 looks like that. So if I take the product of those, I'm going to get a sigma I here, and oddly enough, a minus sigma I here. So notice what we had here was 2 sigmas on the diagonal. Here we flipped it by a minus sign, but this is still going to measure the spin. Well, that minus sign is why this is the spin down, and that's the spin up component of the antiparticle. This is what flips the spins of the antiparticles. The fact that in order to get a spin projection operator that commutes with the energy projection operator, we need to put a minus sign in the projection. So how do we write this? You guys get any questions? You with me? Yeah, okay, good. Okay, so we can use this. Now, let's just try something that contains this. You know, this is a gamma I and this is a gamma 5. So let's just try letting, what do they call it? I think it's called pi in the notes. Pi plus or minus a half identity plus or minus. Okay, I'm going to take a linear combination of gamma alpha, gamma 5s. Let me see which way I wrote it. I think I want, no, that's, I've done it differently in different places. So I'm gonna want to check this in the notes, but I think I want the gamma 5 here. Yeah, flipping the gamma 5 on the other side puts a minus sign, so it changes which is spin up and spin down. You know, that's conventional. We just want to choose it to give us the spins we expect. So we want this to be a spin up state. That dictates which side gamma 5 goes on here. We can fuss with that. But first, let's check that this is a projection. Plus or minus squared. We're going to have a quarter. We're going to have a 1. Plus or minus 2 of these guys, S alpha, gamma 5. And then we're going to have the sign squares away. We're going to have plus S alpha, S beta, gamma alpha, gamma 5, gamma beta, gamma 5. And so let's see what all this does. Okay, if I bring a gamma 5 past any of the Dirac matrices, I get a sign. So this is going to be minus S alpha, S beta, gamma alpha, gamma beta. Gamma 5 squares to 1, so we're done with that. Now this symmetrizes these guys again. And so I'm going to get, let's see. I'm getting a 2 here. Oh, no, I get minus a half times S alpha, S beta times the anti-commutator, which is twice eta alpha beta. And so this is minus S squared. All right, so I need that to be, I'm going to demand that be plus 1, right? I need a plus 1 here to reconstruct this. So already we've determined that S alpha needs to be minus 1. That makes it space-like. Well, we want a space-like vector. Spin is a space-like vector, right? This is going to make it orthogonal to the forward momentum. The forward momentum is the time-like direction, and so now we can project in any of the space-like directions. That's a good thing. Next, we check the commutation with the energy projection. So if I take, let's take P plus or minus here, commutator with pi plus, we're going to have a quarter, commutator 1, what is it, plus or minus P slash over M, commutator with 1 plus S slash gamma 5. And the ones don't do anything. So now we have a quarter and, you know, plus or minus. And then we have P alpha. We have an M down there. We have an S beta. And we have the commutator of gamma alpha with gamma beta, gamma 5. So let's figure out what that is. Okay, so we have gamma alpha, gamma beta, gamma 5, minus gamma beta, gamma alpha. No, gamma 5, gamma alpha. That's this commutator. And let's see, if I push this gamma 5 through, I'm going to have gamma alpha, gamma beta, plus gamma beta, gamma alpha, gamma 5 is eta alpha beta times twice gamma 5. So this gives me plus or minus 1 over 4m. There's a 2, so make it a 2m. Then eta alpha beta means I'm going to get P alpha S alpha. And then there's a gamma 5. All right. That vanishes if and only if P and S are orthogonal. So we get a second condition here, P alpha S alpha equals 0. So as long as S satisfies these two conditions, we can do a projection with this operator, and it will commute with the energy. And right in the rest frame, P alpha is just M and 0, which means that S alpha is going to be anything 0 and some 3 vector S, some unit 3 vector. And in that same rest frame, all right, S alpha, gamma 5 is going to be Si, gamma 5. And we just showed that that's this matrix right here. So in the rest frame, what we get is some unit vector, space-like unit vector S dot sigma. And so in the rest frame, our projection is Si sigma I and minus Si sigma I, like this. And that's the spin projection, right? That's just what we need to be looking at the S component of the spin. So we can take it to be sigma Z and project into the spin up, spin down in the Z direction, but we can choose any other spatial direction as well. And each of those gives us a projection operator. So we can project the spin in any spatial direction, where by spatial I mean perpendicular to the form momentum of the particle. This is much more in line with our understanding of what we're able to measure about spin. Well, I'm out of breath. Let's see. So I wrote a few exercises here. Again, these are quick exercises to get you familiar with what we're doing, so that you can whip through these things as fast as I'm whipping through them here. You know, you want to get familiar with this stuff. If you're going to work with it, you will. Okay, so I can also construct these operators by taking outer products of spinners. In fact, let's see, pi plus. If I haven't done this as an exercise, it might be something for you to do. But I have written here, pi plus is if I take U1 cross U1 bar minus V2 cross V2 bar. I think that turns out to be, geez, let's see. Yeah, there's an H in those. Yeah, the bar has an H, right? So this is an A up, B down kind of thing. So the bar is lowered with an H. So this is going to be A, B, and so on. So we now have a commuting set. Okay, now does pi plus commute with pi minus? There's a quick and dirty answer. They are orthogonal projections, right? So yeah, pi plus times pi minus is 0, right? So the commutator is 0 too. Now, and then the same with p plus and p minus. Those are orthogonal, and we've just showed that the p's commute with the pi's. So we have this set of 4 projections that lets us project everything in sight. We can project out any of the 4 different kinds that, negative energy spin up, anything. So we've got a p plus or minus, we've got a pi plus or minus, and if we take products of these commute. It doesn't matter what order I write them in. P plus pi minus p minus pi plus p minus pi minus. So negative energy spin down, positive energy spin up, and so on. I can project out like any of these I want. So this gives me a way to decompose any general spinner into these different parts. And now, what happens if I add those two and add this and add that? What do I get? Add all 4 of them.
The identity.
You got it. That's right. Right. These are all orthogonal. These pairs are still orthogonal projections, right? Each projects. So if I had, basis spinners, 0, 1, 0, 0, each one of these would be diagonal and project into, one of those, 0, 1, 0, 0 would be, what's that? That's positive energy, negative spin. This one looks like this in the rest frame. And all right, this is a powerful tool in relativity, guys. We can look at these things in the rest frame and see, oh, I totally understand what this means. And we've written these projections in a Lorentz invariant way. So boost to any other frame, all these relations still have to hold. And I'm out of breath, we're out of time. But yeah. Ponder, compute, and email me if you have questions. By the way, Guillermo, nice work on that problem set. I just got his email. 16 pages in licks. Yeah, it was a problem, not an exercise. So yeah, go ahead and get me those things. I know you've been working on them. Ask questions if you're stuck on anything. And then what day is today? Today's Wednesday. So I'll see you. Happy vacation on Friday, your spring break. So, go do something fun, like go climb a mountain or something safe, but, give yourself a breather. You deserve it. And I'll see you guys Monday. I'll stick around if you have questions.
Probably going to keep this problem in my computer for the rest of my life, because man, oh man.
Hey,
I loved it.
Wait till you calculate Baba scattering.
Wow.
There are all these different, electron, positron scattering problems. We'll do those, right? We're gonna keep going here. They're longer, so yeah, you can easily spend a week on some of these problems, right? Getting the details right on a scattering problem. The answers are long, and it's not just Coulomb scattering anymore. There are all kinds of details that depend on the spin and depend on whether it's electrons or positrons, and you get a wealth of new information, new predictions by doing all of this. So it's pretty exciting. But yeah, keep that forever. My favorite 2 courses, they sort of were end caps for my entire college and university career. my first 2 semesters in college, I took an honors calculus course, and that was one of the best courses I've ever had. Then the other best course I've ever had was quantum field theory, and we did all of this stuff. And yeah, those are some books that get well worn. It's a real feeling of accomplishment when you work through some of these things. It really is. So well done on that problem, Guillermo. Yeah, do you have any questions on it? I glanced through everything. It looks like you've done it very carefully. I didn't check, meticulous detail, but I'm pretty sure.
Some small details that I still need to put in, but I mean, the main idea is absolutely there. Like there's like, I think there's like a H bar that I need to like fix. And like carry out.
For the most part, I have set H bar to 1 everywhere. So the way to put them
in
back.
In that case, I'll just get rid of anything I see.
Right. What's that? Sorry. I didn't hear.
In that case, I'll just get rid of an H bar that I see.
Yeah. Set it to 1. I mean, that's totally fair because, we have not kept track of all the H bars. Sometimes we're writing D3K, sometimes D3P. There's an H bar cubed somewhere there, right? Where the H bars and C's go because dimensions have to match, and that's you can find where they go. It's not too hard. Once in a while, it's worth doing. Geez, I remember hearing, I wasn't there, but there some theoretician gave some talk where he had set H bar and C and who knows what else to 1 pi. I don't know. And some experimentalist from the audience says, "Could you put the units back in, so I can, do an experiment with this?" And the speaker says, "No," and the guy in the audience says, "Well, then all your work is useless." So, be able to do it. Okay, that's crucial. You should always be able to put H bar and C back in appropriately, but the answer is unique, right? It is those that, in phase space, the only 2 things you need to give everything geometric units are Planck's constant and the speed of light. That speed of light turns all the times into lengths, and momentum turns inverse lengths. Planck's constant turns momentum, interchanges momentum and inverse length. So you can make everything dimensionless just with powers of H bar and C, and you can put them all back the same way. So give it a little practice, but yeah, the H bar is not a problem.
All right, sounds good. You're on.
Okay, good.
But I was just listening, so.
Yeah, okay, so yeah, I guess we're good here. I'll stop the recording. Okay.